होता ना चालू ना
Good afternoon, everyone. Very warm welcome to all of you for this second session on design of microwave integrated circuit for 5G application. For this session, we have with us the distinguished guest again from JNIT, Dr. Abhay Gandhi sir. Dr. Abhay Gandhi did his BE in 1989 from BRC Nagpur and ME in ECE from Indian Institute of Science, Bangalore in 1991 and completed his PhD in August 2002. After working for 3 years in industry and education, he has joined BRC Nagpur as a lecturer in July 1994. Now, he is a professor at VNIT since 2012. Sir has visited San Francisco, USA in October 1995 to present a paper at an international conference IEEE 95. His area of interest are the areas of his teaching, research and consultancy are analog and digital communication, computer networks, and RFIC design. 10 candidates have completed PhD and 2 candidates have completed MTech under his guidance. Currently, some of the candidates have pursued PhD. He has published more than 65 research papers, mostly in SCI and Scopus journals and international conferences. One of his research papers, co-authored by him, has received the Best Paper Award at Global Wireless Summit held in June 2014 at Atlanta City, USA. He has authored a textbook, Analog and Digital Communication, Theory and Lab Work, published by Cengage Learning, New Delhi. He is a senior member of IEEE and also member of IET and IST. Sir has been a member of Executive Committee of IEEE Nagpur subsection and was the chair of Nagpur subsection for 2025. He has contributed to development of communication infrastructure of VNIT from 1999 till date. He has worked in admission committee for VNIT in 2007 and 2008 as deputy chairman and was member of Central Counseling Board 2010 Technical Committee of VNIT. He has handled multiple designations including Chairman, Education Technology and Library Services Committee, Associate Dean Exam, HOD ECE, Associate Dean Library, Dean Academics, and so on. He has been a member of several MBA committees as an expert. We welcome you, sir. I request our principal, Dr. Malek Khanapurkar sir, to felicitate Dr. Gandhi sir with a memento. Thank you so much, sir. Now I request Dr. Gandhi sir to proceed with the
session. Thank you. And first of all, congratulations to Cummins College for getting approval of this ATAL FDP. Today the plan is that I will cover a few things for about 1 to 1.5 hours, and then my colleague Dr. Arvind Kumar will be taking over, and he will be mainly conducting the hands-on session. Dr. Arvind, please. So I would like to introduce one of the youngest colleagues, Dr. Arvind Kumar, and I don't know whether you have read in the newspapers, but he is among the top 2% researchers as far as San Francisco's Stanford University ranking is concerned. So we are very happy to have him with us as a colleague, and he will be looking after the hands-on session later. Thank you.
Kasturi Patil, ma'am is also with us, ARK Info Solutions. She's from ARK Info Solutions. She's doctorate faculty. Not faculty, she's belonging to
Hi everyone, good afternoon. I'm Dr. Kasturi Patil. I'm from ANSYS, and actually on 26th my separate session will be there. I will give short introduction. I'm working with ANSYS from last 2.5 years. Before that, I was associated with IIT Mandi. I have completed my PhD in implantable antennas, and I have one patent during my graduation that is based on electronic wave radar. So I have published 5-6 papers and few conferences in SCI journals and some conferences in national and international way. So that's how my short introduction. In detail, we will see on 26th. Thank you, everyone.
Thank you so much. I request her to proceed with this.
हम थोड़ा पॉज करो
So, I will just first let me just know like what is the background of the participants. Like all of you must be teachers in some colleges and teaching which subjects, mainly RF antenna and communication. Yeah. See, actually, fine. I mean, I am like coming out with this presentation, challenges in RF design and so on. But the kind of starting point that I have in mind is something like this. All of you, as a student, must have learned electronic circuits. I mean, I'm talking about single transistor or maybe just 2, 3 transistor circuits, common emitter amplifier, common base amplifier, common collector amplifier. Both circuits made out of the BJT as well as field effect transistors. And then we all do all those things, biasing, this, that. But then comes a topic called transistor at high frequencies. And mostly the second year course stops there. है ना? Transistor at high frequency शेवटचा topic. Option ला केला तर केला नाही तर नाही केला. Right? Actually, that is the starting point here. Means whatever earlier circuit design you may have done or whatever assumptions you may have seen or whatever approximations you have seen, they were mainly for circuits or amplifiers operating in maybe at the most few kilohertz or maybe just just some 8, 10, at the max 10 megahertz frequency. So that is where the typical UG course in circuits ends, whether it is, I'm talking about analog circuits, typically where it ends. And this topic which I have now started, now I am going to share a few things with you. Basically, there we will see at every step or at every aspect, we will see that, oh, uh, there we were just assuming it works, but here we have to worry about so many things. So that is the underlying message in this particular piece of experience that I am sharing with you. That when it comes to the high frequency applications, really the circuit design, so fabrication, everything is much more difficult than what you generally do with low frequency circuits. So that is going to be the main part. But of course, why we need that? Obviously, now there are so many applications that are going on, so that is to be done. But then so this is what means very broadly. I would like to cover list of challenges. What is the technology, and then the most important building block, that is the transmitter and receiver, which is there for wireless communication. So that we will spend some time on that, and then we will see how the wireless mobile communication environment makes it challenging, and what are the effects of that on the RF hardware, and finally how all these things have an impact on the so-called RF front end that we design or we use for wireless communication. So this is actually the first part of my talk, and if time permits or whatever, I will come to the second part, which let us see. Like I am not really sure whether we will be able to cover that or not. But there is some like other part of this also. But it's some kind of a subtopic under challenges. So that we will see later. Okay, so first I think it is important that we really define what is RF, radio frequency. So very simply, that is the frequency at which we are going to do radiation. We are going to create a signal at that frequency and we are going to feed it to an antenna and then it is going to radiate. And of course the reverse process will happen at the other end. So that is RF. And it has evolved over the years as the different applications are coming up and they are getting developed. The meaning of RF keeps on changing. If you go back in very early days of broadcast radio, maybe in somewhere in 1940s, at that time amplitude modulation radio broadcasting was there. So RF frequency means it could be just a few hundred kilohertz, starting from around 400 kilohertz all the way up to 8 megahertz. That's all. So that was the meaning of RF at that time when they were designing broadcast radio and those things. Then FM, television, and then mobile phone. So as these different applications started coming in, the meaning of RF gradually changed and it kept on shifting to higher and higher frequencies as the new and new applications started coming into the market. So here I would still be focusing mainly on the 1 to 10 gigahertz range. Although things have gone well beyond 10 gigahertz also, it has not stayed there. Beyond 10 gigahertz, we have millimeter wave and then terahertz and those things. But so far, I haven't seen really the circuits operating in those frequencies coming up in a big way. I mean, they still remain some kind of a specialist or a special thing. But up to 10 gigahertz, the circuits and the associated components and everything now they are fairly common. We are already using Wi-Fi at 5 gigahertz band and things like that. So up to 10 gigahertz, roughly, things are bit common and accessible. Beyond that, it is a bit exotic kind of technology. So again, the challenges are at three places. One is variety in everything. We'll come to that. Like variety in what? So it is in everything. We'll come to that. Then circuit design and fabrication was the part I was referring earlier. That it doesn't no longer it remains simple. You have to consider many things. So that is the kind of second class of challenges. So these are like three classes of challenges. One is variety, another is circuit design and fabrication, and third is the wireless communication environment. That is the third challenge. So let us take up these one by one and see what happens. So main reason is for variety is coming in is the variety of applications. So many applications now going on already. Mobile phones within that, 2G to 6G, all these generations, Bluetooth, Wi-Fi. Then you have other wireless technologies, IoTs, wireless sensor networks. So many applications, and each having its own frequencies, right? The frequency bands to operate. So because of that, like different applications, different frequencies have been allocated to them, and you have to tackle them in a product at a time. Like I don't know, like you have noticed, but the mobile phone itself is a very good example. It is dealing with so many things. Apart from being a mobile phone, it is having Bluetooth, it is having Wi-Fi, it is having a GPS receiver, it is having FM receiver, and some of them also have the so-called NFC, near field communication. Even that type feature is also there. So just single device is handling so many different frequencies and applications. So handling all these things at the same place is a challenge. Then variety of bandwidths, variety of data rates, variety of modulation methods. Then the variety in medium sharing mechanism, and that is again like something essential because when it comes to wireless communication, then you are talking about a shared medium. So there has to be a mechanism to share that medium among different transmitters and receivers. So that is also another place where things become like there are varieties. And finally, transmitted power, different transmitted power levels. And as the transmitted power levels are different, the amplifier design also changes completely, right? So which kind of device you can use, what are the other things you need to do so that the transistor and that amplifier is able to handle that power. So now you are all familiar with these applications. I don't think I have to really go through the whole list. And even in relatively low power applications, these are there. And these two are relatively less encountered applications. Satellite, of course, if you are using dish antenna and DTH, if you are having at your home, you are already using the satellite. But deep space communication and radio astronomy is something not really everyone gets access to, or everyone gets to work with them. But they are also equally important applications. So in when we say deep space, that means at least having means much beyond Earth, like much beyond what satellites are. Okay, means something like moon and beyond. Okay, so that is deep space. And radio astronomy is again another very important area where the radio signal coming from different stars and quasars and whatever you are catching that signal and doing the processing. So the variety of applications is one big challenge actually, especially when you have to handle multiple applications or multiple receivers at the in the same box or on the in the same product. Then these building blocks also, I am sure you are all familiar. So antenna is something I think Kothari sir has told also someone in the morning. Then you need to have these other parts. These are the kind of bare minimum number of modules that you need for building a RF transceiver. So you need antenna for both transmitting as well as receiving signals. Then there is something called low noise amplifier. So the meaning is that when you design this amplifier, it will generate on its own. It will generate as less noise as possible because it is there to receive very weak signals which are incident on the antenna. So in order to amplify such signals, the amplifier itself should not generate excessive noise. It will generate. There is no doubt about it. In fact, every circuit operating at a temperature above absolute zero will generate noise. So only thing is how much you control it, how much you keep it below an acceptable level, so that the signal is amplified and then you are able to work with it further. That is actually the only question. So low noise amplifier is required on the receiving side and power amplifier is required on the transmitting side, because you have to transmit the RF signal and make it reach at the other end. And then you need some duplex in the sense that typically this is associated with sharing the antenna, because you have the same antenna for both transmit as well as receive. So to share the antenna, you need this kind of arrangement. And then mixers and oscillators, again you need them for the so-called frequency up conversion and down conversion. Again, in somewhere, I'm sure all of you must be familiar with the super heterodyne receiver, isn't it? Like you have local oscillators and then incoming signal, then the IF amplifier and things like that. So the same thing is used here also. And the signal at low frequency is kind of converted, means up converted into higher frequency and transmitted. And similarly, the incoming signal at higher frequency again it is down converted and then processed further. So the superheterodyne principle is very important. It is used very widely in this RF circuits. So these are some of the just the components. Again, I am sure many of you have heard about them. The resistor, inductor, capacitor. I mean, what's the big deal? They are there is from second year or first year network theory course, right? But we will see down the line that special efforts have to be taken to fabricate these resistor, inductor, capacitor for RF circuits. Okay. The main problem is if you really go into the details of the KCL and KVL, Kirchhoff current law and Kirchhoff voltage law, then actually that law is kind of it holds if the speed of propagation is infinite. Actually, means if you build a circuit, let us say which is 4 kilometer distant or hundreds of kilometers long, then the behavior of that circuit actually does not obey KCL KVL because the propagation speed is finite. There is a simple derivation also about this, but now I don't want to go into those mathematics. But it can be proved that KCL KVL hold only if the speed of light is infinite. Practically, speed of light is a very high number, but it is a finite quantity, right? So only for short dimensions or small dimensions compared to wavelength. Okay, this is the most important thing, that at short dimensions compared to wavelength, the KCL and KVL are obeyed properly in the circuits. But moment the dimensions are much, it means even if comparable to the wavelength, even if they are about maybe just from 1% of the wavelength onward, if the dimension of the components happens to be like that, then you have to treat it as something else and not as a circuit component. So this is a very fundamental requirement. And so what happens when you start thinking of building a circuit, let us say for a 5 gigahertz circuit, now or 6 gigahertz. What is the wavelength at 6 gigahertz? Yeah, how many millimeter or centimeter?
Millimeter.
No, how many?
Less than 1 mm आसपास में.
कारण थोड़ा कैलकुलेशन का प्रॉब्लम है.
0.05 mm.
0.0 होता है इतना नहीं. 0.05 मिलीमीटर असेल.
Millimeter.
3 into 10 raised to 8 meter per second divided by 6 into 10 raised to 9. 3 by 6 is 0.5 into 10 raised to minus 1 meter.
Meter. 0.05 meter.
म्हणजे 5 mm.
5.
For such a small wavelength, the size of the component should be even smaller than this. Okay, then only they will behave as the so-called lumped element or lumped parameter elements. Like if you are building it as a resistor, then it will behave as a resistor only if the dimensions are very small. Okay. Another big challenge associated with passives is that there is always something called some parasitic effect associated with passive copper. I will just give you an example. All of you are familiar with that BB resistor, right? You have that. This is the PCB, and then you have this. It is mounted on the PCB like this. That resistor looks, if you look it by the side, and then there is a lead, and again it goes through the PCB and you solder it here, right? And this is soldered here, and then this is got that those BB color code on that. This is the magnified view of that resistor. Now, this will behave as a resistor only at low frequencies, because at high frequencies what will happen, even this lead, it will have its parasitic inductance. Both these leads, they will have their parasitic inductance, and because of that, and I'm sure you remember inductance, like J omega L means the reactance increases in frequency, right? So what will happen if you try to use the same resistor at higher frequencies? The impedance of this parasitic inductor itself will start increasing, and it will become comparable to what that resistor is doing, and later on it will be at higher frequencies, it will be on higher than that. Okay, so this is just one example that parasitic means what? Means you don't want it to be there, but it is there. Okay, so that is parasitic. So you have to fabricate the components in a totally different way when it comes to art. Okay, in fact, they do what is known as the leadless. There is no lead. Like if you look from the top side, then there is a track. There is another track, and then you put the component on top of this, and below that there is a paste, so that when you heat the overall product, the soldering happens over here below the component. Okay, so there is no means there is no drilling of the hole, nothing. The resistor is, or inductor, capacitor, whatever, it is soldered directly on the track. Okay, so that this lead is not there, and there is no parasitic inductance of any kind. So whatever we even don't bother about at low frequency, everything starts showing up its undesired effect if you try to use it for high frequency, and then you have to redesign those components in a different way, and your whole circuit fabrication approach, the production machinery, everything changes, because the components are very small in size. They are just hardly a millimeter or just 1 or 2 millimeter in dimension. So handling them becomes very easy, very difficult, and soldering, everything changes completely, right? And means when we conduct this course in VNIT, I spend a lot of time about just resistor, inductor, and capacitor. And that too, whatever I have mentioned is only at board level. Then you can go inside the chip, and again inside the chip there are many other problems. Okay, the parasitic capacitance with the chip substrate is the biggest problem, and like because it is capacitance, again it keeps or limits the useful frequency of the both all the three RLC, resistor, inductor, capacitor. So the thumb rule is every passive component will have some parasitic effects, and it will have something called self resonance frequency. Okay, there is some inductance associated with it, some capacitors associated with it. I am telling you this is the thumb rule. I am not saying that it will happen everywhere, but generally every passive component will have its own self resonance frequency, and you have to make sure that whatever is the operating frequency you have in mind, the self resonance frequency is much higher than that. Okay, so what does that mean? If I am trying to design an amplifier and I am trying to use an inductor in that amplifier, let us say the amplifier is designed for 5 gigahertz, then I will need an inductor whose self resonance frequency is much higher than 5 gigahertz. Okay, maybe some 8, 10 or something like that, much higher than 5 gigahertz. Then only it will be useful as an inductor in my circuit, right? So that is the most important kind of consideration when it comes to this resistor, inductor, and capacitors. So as I said earlier, we take them for granted at low frequencies. If it is a BBY 1 kilo ohm resistor, it will behave as a 1 kilo ohm resistance. But at higher frequencies, everything starts behaving differently. Okay. So in some applications, people have also tried to use transmission lines as a circuit element. I'm sure you remember quarter wave line can behave as a capacitor or inductor and things like that. So that also is an option available. But my experience is that when you try to use this transmission line as an element, it occupies a lot of space on the board compared to the lumped parameter elements. So only if there are other issues like something like power handling issue or something, then only you can go for the transmission line based component. Otherwise, it's better to use the discrete components. Again, this I am this is applicable only when you are talking about board level circuits. When you are going chip level, then it is a totally different ballgame. Then SIW, of course, I am sure Arvind knows much more than me as far as SIW is concerned. It is surface integrated waveguides. So they are also used at board level or very high frequencies, maybe the like how much above 6 gigahertz or something SIW? About 10. About 10, yes. Because what I understand is as the frequency goes up, the dimension reduces. So then you can use them in the circuits. Okay. Otherwise, traditionally, if you have handled that klystron and those gun diodes and everything, I am sure you have seen those waveguides which are having very large dimensions, isn't it? But as the frequency increases, the dimension comes down, and then you can use them as some planar element. Okay? So that is what is. So that was about passives. Okay. So it is not a simple thing here. And again, in active also the normal transistor that is available is also not useful. Okay, I will maybe down the line I will mention that how that is the case. So we use some different type of transistor here. This is gallium arsenide as a material. Then this is high electron mobility transistor. Okay. So gallium arsenide as a material. So if you have noticed, apart from silicon, there are other materials that are also equally important. And then this is high electron mobility transistor. Then this is pseudomorphic high electron mobility transistor. Then there is silicon germanium HBT heterojunction bipolar transistor, and then silicon germanium MOSFET, and then very exotic materials like indium phosphide or aluminum gallium nitride based transistors. So right now, I mean, I don't know whether you have heard about this or not. But anyway, we are going to spend some time after this. But at least the key takeaway from this slide is that the normal silicon MOSFET is not enough, or it is not really useful. And there are many other options, both in terms of transistor geometry, fabrication, and material. So all the three things, okay, transistor geometry, the way it is fabricated, and the material. Okay. So I don't know, there is some request for a 5-minute break, so I will take a break and then we'll continue. ते सिलिकॉन आभार असतो आणि त्याचा इंजिनिअरिंग म्हणजे आयडेंटिटी बेसिकली वॉटर बॉटल बेस एलिव्हेटर जंक्शन ते हिटो जंक्शन असतं केमिकल साईडचं जे असतं ते त्याची बॅक्टेरिया जास्त असते आणि कमी असते तर त्याच्यामुळे लिकेज करंट कमी होते आणि एलिव्हेटर एफिशियन्सी वाढते आणि मुख्य म्हणजे बेस इव्हन छोटा जर केला ट्रान्झिस्टर साईज छोटा जरी केला तरी त्याचा परफॉर्मन्स मेंटेन राहतो ऍक्च्युली काय मेन बँडविड्थ प्रॉडक्ट आहे ना ही ट्रान्झिट टाइम तर ट्रान्झिट टाइम कमी करून ट्रान्झिस्टर छोटा आहे तो छोटा केल्यामुळे बेसचा रेजिस्टन्स वाढतो तर तो कमी करायला कॉम्पेन्सेट करायला स्टेट खूप लांब आहे
initially they can see. After that they can continue. But if you want to go to before that, you should have because designing it was like that, more video
So we can continue. So this is just an introductory kind of slide. I will cover some details in upcoming slides. So, these points I have already mentioned that when it comes to the passive components, they are equally important as active. You cannot just take them for granted. Then size versus wavelength also I have already mentioned that KCL, KVL will be varied only if this condition is satisfied. Yeah, this is somewhat important. Chip level versus board level. These are the These are the typical design choices that are available for RF, and the overall procedure and the approach and the possibilities all are different. Okay, so we are familiar with board level designs. Like we purchase those resistor, inductor, capacitor, whatever different switches and transistors, and then we solder them on the PCB and things like that. So that is something we are already familiar, and same thing we can think of for RF also. But as I mentioned earlier, the fabrication method is totally different because the component physical design is totally different. Soldering method, handling the component, everything that is different. But still you can do at board level. Another very important thing to be kept in mind when you are working at board level is that when you are planning for your circuit fabrication, many of these websites, whether it is DGT or Mouser or many of them, they typically ask for minimum quantity. Like if you go and see the price, they will say 50 paisa. But then they will say for minimum 10,000 or for minimum 1,000. So like that, they will mention the price. So you have to check that what is the minimum order quantity they are expecting, what is the delivery time they are kind of mentioning, and accordingly you have to plan your RF project. So I mean there are a lot of non-technical challenges in this, and after you receive the components, then of course you have to arrange for their soldering and all those things. But at least at board level, you can procure components from different like vendors and think of building a circuit. But all these RF circuits, they are not designed just like that. Typically, we have to like simulate our design and validate our design through simulations. So when a manufacturer is selling those products, you also need to get their simulation files also. Something related to simulation. Either it could be an S2P file obtained by actual measurements done on a DNA, or you need some spice model. Okay, either of these two, either the spice model for inclusion in the schematic simulation, or S2P model to be included in the simulation. One of these two is required, because then only you can include that component in your software. Software you use typically are like AWR that you have here, or there is another very popular software that is ADS by Keysight. So all these softwares are used for RF circuit design, and these board level component details also must be available to you so that you can plug them in your design and simulation and then complete your circuit. So the component should be available, it should be within your budget, it should be within your time budget, and its documentation in soft format must be available. If all these requirements are met, then only you can think of going at board level, right? So these are the broad guidelines. And when it comes to chip level, then it is a totally different game. You have to have some tie-up or some agreement with some fab. The ones which I am aware of is one is the so-called Euro practice, which they have some fabs in Europe, and then of course TSMC. You can ignore TSMC, Taiwan Semiconductor Manufacturing Corporation. So you need to have tie-up with them, and then you need to have tools like Cadence RF Spectre or maybe ADS, and then you have to sign one NDA with them, with the fab, that no non-disclosure agreement. Then they will share the model files and the schematic symbol and everything, all those libraries they will share with you. So now you can include components only what the fab has given to you. So your library which comes from the fab, only that is your choice. And out of that you pick up, build your circuit, first the schematic, then the physical design, and ultimately you have to generate a Gerber file which describes the full layout of your circuit, and then It goes to the fab and then you do the so-called takeout, and then they will fabricate it on the wafers, and wafers, either raw wafers can come back to you, or they can break those wafers into small ICs and they can package them also. So either you can get packaged ICs individual, or you can get it on a raw wafer, and then you can test it, and if it is okay, then go ahead and make it as a product or whatever. So this is the typical flow for the chip level design. Then this also I already mentioned, transmission line versus discrete components, and yeah. So the main role of these passive components is into this filtering, feedback network, and biasing network, and impedance matching. Again, impedance matching is a big thing in RF, because when the RF signal is going through the overall circuit, it is a very, very precious commodity. So you don't want to use RF signal to it getting diverted away from signal path. Suppose there is a signal path and there is a biasing network. You don't want that the RF should go into biasing network. Then by ensuring proper matching, you don't want any reflections, because that is also a kind of signal loss. That when you send something to the other end, it should be absorbed there. Nothing should come back. Otherwise, it is defeating the purpose. You want that the amplifier should amplify all the input signal, so that is not happening. Part of it is coming back. Or you want that the antenna should transmit everything, but part of it is getting reflected. So you don't want this to happen. So for that, this impedance matching is very, very crucial when it comes to these RF circuits. And as the frequency goes up, all these ensuring all this matching and everything becomes very difficult actually. So that is the these are the issues associated with passive components. So these are some of the options that are available for fabricating these passive components, like resistors. You can the so-called thick and thin film technology, and if I remember correctly, thick film is more very similar to the screen printing kind of technique, and thin film is very similar to IC fabrication. And then when it comes to polysilicon, it is completely coming out of IC fabrication technology. So many resistors, they are called as chip resistors. So the meaning is that they are fabricated. I mean, they are fabricated by using technologies like this, either thin film or maybe the chip making. But then they are packaged as individual two-terminal devices, okay? And then you can solder them on your board and use them as a resistor. But while manufacturing, they are manufactured as if they are, by using chip making technology or very similar technology. Then when it comes to building capacitors, of course, the most simple geometry is the so-called parallel plate capacitors, and it is very easy for silicon manufacturing also, because you have got a wafer and then you build different layers. So you can always have two layers and metallic layers, and separated by some dielectric, and you get capacitors. So parallel plate is a very commonly used geometry. But there is also something called as lateral flux capacitance, and that happens at the chip level. So the meaning is like this. I don't know whether you have seen, but you can think of a geometry like this. So this is the top view of some metallic piece. Okay, so you can fabricate it like this. So this is one metallic piece or metallic track, and then you can have another. this is the top view of two metallic tracks or two metallic shapes. One is like this, another is like this, and they are very close to each other, but there is no contact, there is no physical contact. Okay, they are very close to each other. So if like this is having a higher voltage than this, then you will get field lines like this from positive to negative. You get the field lines. So these field lines, they are parallel to this plane of or the surface of this board. Okay, so they are called as the lateral flux capacitance. Okay, so the in a parallel plane, what happens? Like suppose these are the two parallel plates. Then the electric field lines, they are starting from one plate and ending on another. Okay, so this is referred as the vertical flux. But when it comes to lateral flux, the electric field lines are parallel to the surface itself. So this is another option that is possible only at chip level, because you need to have very close spacing, like fraction of micrometer or something, that you need in this particular case. So this is sometimes I have seen people doing this at board level also. This kind of design, it is called the interdigitated design. Interdigitated design, because digit means finger, so it is like your fingers like this. So interdigitated design. Sometimes I have seen people doing this at board level also. I'm not really sure how effective it is, but at chip level, this is a very popular option. And then the capacitance depends on how is this the so-called perimeter of proximity. Okay, how is this? How long this perimeter of proximity is, and then people have tried out even the fractal capacitors also, because as you are aware, or you may be aware, that fractal shapes are very, quite random in nature. So they can achieve very high perimeter of proximity when implemented in a area like this. So I mean, these things have been tried out at the chip level in these RF circuits. Then coming to inductors and transformers, again, for us inductor means some wire wound coil around some cylindrical form or things like that. But that is not physically it is very difficult at chip level. At chip level you need everything to be planar. So the very commonly used geometry is the planar spiral geometry. So what you do is you take a track and then something like this. So this is one end, and this is another end of the inductor. So now gaining access to this end of the inductor is easy because it is in the same plane. But when you want to gain access to this end of the inductor, then you have to have the so-called via or via, so that you can make a contact with the layer below, and then so this I am showing as the lower layer. So then there will be a track in the lower layer with which you will gain access to the inner terminal of this spike. Right. So this is how we implement inductors at RF in the chips. Okay. So that is called as the planar spiral. And of course, as I mentioned earlier, you can always use the transmission lines also as inductor if the situation allows. And then there is something called a bond wire. I'm sure some of you are aware of this. This bond wire is essentially if you open an IC, actually inside there is a die, and from the die up to the external pins of the IC, these bond wires are used. So they can, their inductance or self-inductance can also be utilized in the chips. So that is the meaning over here. Okay, and these passive components, they introduce extra loss and deteriorate the noise performance. Why? Because every resistor, now whether you have introduced it in the circuit or if it is a parasitic resistance, because every metallic piece will have some or the other resistance, although very low, but it will be there. So every resistor, whether you have introduced it intentionally or whether it is parasitic, will always be a source of thermal noise, right? And as I said earlier, every circuit operating at a temperature above absolute zero will have thermal noise. So all these intended and parasitic resistors, they are sources of noise, and then you have to analyze everything and then design it in such a manner that their noise is under control. Then about antennas, I won't spend much time. I'm sure all of you are familiar. So planar antennas is a big topic. Like almost everyone is making these antennas, patch antennas, and all this. And I'm sure that it will be covered in your earlier class or maybe in the future. So you can have fixed antennas, also called conformal antennas. That means they are able to take the shape of some other object. So that is conformal antenna. Then there is the introduction of partial ground instead of having full ground below the radiating patch, the partial ground. Then reconfigurable antennas, single band, multi-band, ultra-wideband antennas. Then use of metamaterials and dielectric resonant antennas. So even I am sure Kotari sir must have introduced these things in the morning session. Is it, did he cover these things?
Yes.
Some topics. Yeah. So I won't go into each and everything, but here I have just listed them that what are the different things that are being used currently. Okay, so just to create awareness, I have just included them in this. Yeah. So as I mentioned earlier, okay, let us take a slightly diversion, from the slides. I am sure you have heard about the so-called gain bandwidth product of a transistor, right? And that really decides what is the useful frequency range of the transistor, because theoretically it is that frequency where the antenna gain becomes 1, isn't it? Because as you start operating the antenna at higher and higher, amplifier or transistor at higher and higher frequency, after some frequency the gain starts coming down, and then it is 0 dB or 1, and that's it. So that is the gain bandwidth product. And see, transistor means that transistor is supposed to amplify, so it should provide some gain, isn't it? So you have to operate it at a frequency much lower than its gain bandwidth product value, isn't it? Like suppose the gain bandwidth product says it is 10 gigahertz. So that means at 10 gigahertz its gain will be equal to 1. But you need higher gain, so you need to operate it at a much lower frequency, isn't it? You need to operate it at maybe some 3 or 4 gigahertz. There it will offer some gain, isn't it? Because then from 4 gigahertz it will go down to 1. But at 4 gigahertz there will be some gain, right? So this typically you hear in the context of BJT, where that gain is actually the current gain. That HFE, right? HFE or forward current gain in common emitter configuration. So that HFE going to 1 is the like extreme thing that is happening. But we need that if it has to work as an amplifier, it should have a much higher value, and then that means you have to operate it at a much lower frequency. So operating frequency and this cutoff frequency, okay, or FT. Some of you must have heard about it. The subscript capital T. This is also an like indicator that what is the useful frequency range of the transistor. So the point is that as the operating frequencies are going up, like we started with 2G mobiles, 800 or 900 megahertz. That means less than 1 gigahertz. Then we came to Bluetooth and Wi-Fi, 2.4 gigahertz. Then Wi-Fi also was available in 5.7 gigahertz. So as this operating frequency is going up, we need transistors with even higher and higher cutoff frequency, or even higher and higher gain bandwidth product. Then only they will be useful at these operating frequencies, right? So how do you increase this operating frequency, or how do you increase the cutoff frequency of the transistor? The simple game is that this FT, is inversely proportional to the transit time of charge carriers. This FT is, I'm just taking FT. Actually, there are other definitions also. There is another definition is Fmax, where the power gain goes to unity. There are many other definitions of the gain, but I'm just, because you are familiar with this, I'm continuing with FT. So whatever is this cutoff frequency or the maximum frequency, they are all inversely proportional to transit time of charge carriers. What does this mean? If the transit time of charge carriers has to be as small as possible, that means the device size has to be as small as possible, isn't it? The charge carrier should not be required to go through a very long kind of device. They should be required to go through a very short region, okay? And they should be going through that with as high speed as possible, right? So this transit time tau is equal to the device length divided by velocity, whatever, or speed if you like. So this FT will be then proportional to reciprocal of this transit time. So it will be proportional to velocity divided by length. Okay, what does this mean? It means that if you are talking about a BJT, bipolar junction transistor, the base region should be as narrow or as small as possible, and somehow the charge carrier should go through that at as high frequency, as high speed as possible. If it is a field effect transistor, channel length should be as small as possible, and the charge carrier should go through as quickly as possible. What decides the speed of the charge carriers? The mobility, isn't it? So you should have as high mobility as possible for the charge carriers. Okay, and what does that mean? You should choose a material where the charge carriers have high mobility, right? And that is why instead of silicon, you see other materials also coming. Okay, so the entire game of RF transistors is only focused on this part, that try to make or try to have as high speed as possible for the charge carriers
and try to fabricate as small as possible. The device should be as small as possible. That's all. And for that, do everything that is possible. Okay. So using advanced photolithography, try to make as a small transistor as possible. Using materials with higher mobility, try to fabricate the transistor. And then you have some advanced fabrication techniques, the so-called heterojunction fabrication techniques that also enhance the performance further. Okay, so heterojunctions are used both in BJT as well as in these field effect transistors. But the end purpose is that the mobility of the charge carrier should be boosted, it should be increased further. Okay, so whatever different types of materials and transistor geometries you are seeing, the driving principle is this. So as you can see here, silicon, the standard semiconductor, then gallium arsenide. This is an alloy of gallium arsenide and aluminum arsenide. And then you have other materials like indium phosphide, silicon carbide, and gallium nitride. Right. So these are the materials that are available. What is the additional advantage of silicon carbide and gallium nitride? I'm sure
High mobility.
high mobility is there, but there is one more advantage because of the large energy band gap. They can operate at higher power levels. Breakdown voltage is very high, so they operate at higher power levels. So in fact, gallium nitride is a big thing now because they can operate at high power, high frequency at the same time is very difficult to achieve. Okay? So that's why gallium nitride has acquired a huge importance, especially in defense, because you need to generate very high power signals for radars, and that is possible with this gallium nitride. Okay. Then transistors, again, you are all familiar with bipolar junction transistors, so BJT is there, but instead of normal transistor, you can always fabricate the so-called heterojunction bipolar transistor. So what we mean by heterojunction is that the base emitter junction consists of two different materials, but their lattice, they don't mismatch much. So you can fabricate or create that junction, and that has got certain advantage. Okay. Now I don't want to go into too many details because there is too many details here as far as this is concerned. But at least you know that there is something, some bipolar transistor where the base emitter junction is of two different materials. Basically, you need that the energy band gap in emitter region should be more than the energy band gap in the base region. That is the basic requirement. And to achieve that, we do this. Then there is something called MESFET, metal semiconductor field effect transistor, that uses a Schottky barrier to modulate the or control the channel current flow. And out of that, then we build this high electron mobility transistor and things like that. So these essentially all these three, whether it is silicon germanium MOSFET or this PHEMT or HEMT, the common thing in all these three is that ultimately create a very thin layer where the charge carriers have got very high mobility. Okay, so here you see the name itself is high electron mobility. Okay, so there is a special region in the channel where the electrons have higher mobility than normal. Okay, and that is achieved by proper fabrication, because I hope you remember that the energy band diagram completely depends on the interatomic distance, and when you alter the crystal structure, the interatomic distance changes, energy band diagram changes, and that really results into this high electron mobility region formation. Okay, again, I am not going into details, but this is essentially the concept. So, and again, high electron mobility is to be linked with high velocity, isn't it? So, choose a material. This is typically implemented using gallium arsenide or some alloy. So, choose a material and advanced fabrication technique, that combination gives you very high mobility. That is the meaning here. And similarly, silicon germanium. So it is the silicon germanium alloy layer in the channel region. Again, that offers a region of very high mobility. So the transistor is able to operate at RF. So the key takeaway is that the normal transistor is not at all useful, and a lot of efforts are required for fabricating the transistors that operate at higher frequencies. And that's why these transistors and all this hardware is very costly. It is not so easy, or it is not even cheap also. Okay, so I think I will continue for about 15 minutes, and then we'll start with the hands-on session. Some of the points you are already familiar with. Uh, like in this trend also you are familiar that everything is being miniaturized, and the idea is that either you do more in same space or do the same in less space. This has been the trend. Another very important thing about RF technology is that because most of the devices are battery operated, you have limited energy availability, and because of that, you have to again design the circuits that have very high power efficiency. Otherwise, they will just drain the battery quickly. So that is one more constraint. And making all these exist in the same substrate, that is also a big challenge. RF, DSP, other digital circuits on the same substrate is very challenging, because RF part is very sensitive to noise. And as you are aware, digital part is all switching transistors on and off. So they create a lot of noise, and that affects the RF part. Okay, and the challenge for the low noise amplifier is to amplify signals in microvolt range. So that problem becomes even more difficult if there is DSP and other circuits in the same substrate. So that is one more challenge. This coexistence is also a challenge. Okay, so I will go through all the points. What the takeaway of this slide is that all this RF technology started with military applications, but then gradually they shifted into the commercial world. So when it was being done for military applications, no one really bothered about the cost. But when it comes to commercial applications, then you have to worry about the cost. And then you don't get to use very good materials like gallium arsenide or something. You have to do the same thing with CMOS. Okay, because CMOS is the thing, it is already being used for the digital hardware and it is so common. So how you can build RF circuits using CMOS? That is also a challenge, because it is relatively easier to design with other materials like gallium arsenide. But with CMOS it is even difficult, because the parasitic effects in CMOS are more, and the silicon itself is not a really very high performance material. So the only thing that has saved CMOS is the scaling. As the transistor size has reduced and the channel length has reduced, they have been able to push the CMOS performance to the acceptable level. That is what has happened. Then this I have already mentioned, so I will not go through this again. This also I will skip now. Basically, what it means is that in the layered architecture, the RF is working at the bottom of this layer architecture, that is the physical layer. Yeah, so this is how a transceiver looks like. You have the antenna, then there is a bandpass filter at the input of the low noise amplifier. Then you have to have the so-called image reject filter. I'm sure you have heard this problem that when you build a super heterodyne receiver, you also have the problem of image frequency. So to reject that, you need this image filter. Then there is a mixer, and this is meant for down conversion. So the incoming RF signal is mixed with this. So here you will get both the frequencies, the addition of frequencies and difference frequencies. And difference is what will go through because the intermediate frequency amplifier is tuned for that. So it will allow only the difference frequencies, and then you will have another amplifier with automatic gain control. And once that signal is available, it will go through A to D conversion, and the DSP will take over. Okay, the digital signal processing will take over. And on the transmitting side, there will be D2A converter. Then you will do some basic filtering, and then it will go to another mixer. Here, the addition of frequencies, that is what will be amplified by the power amplifier, and it will be transmitted. Typically, in some applications, you could have a low pass filter here, but frankly speaking, I haven't seen anything between power amplifier and antenna generally. Okay, but some applications may have this, and generally you connect the power amplifier directly to the antenna. So this is the transceiver, and this is still analog RF hardware built using amplifiers consisting of just 2-3 transistors. So whatever you study as a UG student in second year, circuits with just 1 or 2 transistors, same thing is happening over here. Okay. Typically the LNA will have just 3-4 transistors. Power amplifier will have just 2-3 transistors. So that discrete transistor design is still required in RF, because elsewhere you have op amp, isn't it? Like you just take an op amp and addition or filter, whatever. At low frequency we have op amp, but at high frequency we have to use these transistors. So this is the example of a transceiver front end. So what concept here is that for transmitting, you are using one frequency band, like for transmitting you are using 1880 megahertz, and for receiving you are using 1960 megahertz. So you are using two filters, two bandpass filters, one for transmitting, another for receiving. So by using two bandpass filters, you are kind of ensuring that the bidirectional communication is happening. So this is just an example of the frequency division to plane, that how you can ensure bidirectional communication with a filter. Okay. So actually the second part of it was the effect of wireless communication or wireless mobile communication. So I will try to cover it as quickly as possible. Because this is pertaining to when the RF circuits are used for communication purpose. I mean, that is the underlying assumption that whatever RF circuits we are talking about, they are being used for communication. So then these issues are there, that first thing, inherently a shared medium, then you need to have some sharing mechanism. Then security is a big issue, because when you transmit a signal, you never know where it will go and who will catch it. And similarly, you will never know that who will try to interfere with your system, right? And you also need to have protection from interference and noise. I am sure some of you may recall recently there was a lot of delay of flights in Delhi airport, right? And it was there was a news that it was due to GPS spoofing. That means someone sent like a spurious GPS signal, and see, the GPS signal which is coming from the satellite, that is very weak. But if there is a nearby transmitter which transmits similar signal but with very strong, so the circuitry catches that signal. and that was sending the totally wrong information. And you can literally play havoc with the navigation system of these aeroplanes. Okay, like you can be in Delhi, but you can send a signal which will make the aircraft think that it is in Mumbai, and then accordingly they can like come out with some wrong settings which are not applicable here. So I mean, just I recall that recently that has happened. It is based on these things, okay? Security, sharing, all these things. So let me just see what like summary I can take out here, because this is covering a lot of basic issues. So I would go with that. Yeah. So the one major problem in wireless communication is of course the multipath propagation. That means when the signal starts from the transmitting antenna, it will reach through multiple paths at the receiver, and then there will be superposition of them, and you will get different or distorted version of that. So like sender has transmitted just two pulses here. This sender has transmitted just two pulses, but they arrive at here as multiple copies. That is the multipath propagation, and that has a big impact on wireless communication and also on the RF hardware. Why I have included it here, because all this has got direct impact on the RF hardware. So that I will just try to mention. Yeah, so only this part I will mention and then stop. How the wireless communication has impact on the RF circuit. So low noise amplifier, what is the minimum power it will get for amplifying? That depends on what is the transmitted power, how the antennas are designed, what is the overall path loss. So that will have impact on the LNA specification. Then unfortunately, in wireless communication, the transmit power is limited by many things like interference limitation, safety, intended coverage. So, whatever RF circuits you are going to build, they need to operate within these constraints. The input SNR of the low noise amplifier, that depends directly on the environment. What is the desired noise figure and gain, that also depends on the environment in which the LNA is operating. Then power amplifier, there is a major choice whether it is a constant envelope modulation or variable envelope modulation. Then if you want to use pre-modulation filtering, fine, but then the power amplifier will have this problem of spectrum regrowth. That means it will transmit again in those frequencies where it is not supposed to. So that is called as the spectrum regrowth. So that comes, I mean, that is avoided if you maintain proper linearity of the power amplifier. Then it has to meet a lot of interference related specifications. Peak to average power reduction is required to maintain linearity, battery and power added efficiency, reverse link budget. All these have direct impact on the power amplifier specifications. Okay. So I will just stop here. This was only one part of first part of my presentation, but I think it is enough. I had another topic in mind, but maybe later. So these are the points that we have seen. There are several challenges in RF design. I hope you agree with that now. And the wireless mobile communication environment, that also has huge impact on the specifications of the RF front end, and the newer technologies, the software-defined radio, cognitive radio, these challenges have become even, the variety has been added. But of course, I mean, the challenges have been solved. I mean, people have worked, and all the products, all the hardware gadgets, they are all working. So it is not that it is like you cannot do it. People have done it, but it is not so easy. That is the point here. So I think I will stop here. And if there are any questions, fine. Otherwise, Dr. Arvind will take up a specific case of an amplifier design. So, any questions or anything?
Thank you so much, sir, for the session. As mentioned by sir, sir has covered the topics regarding the design and challenges in RF design, including the components involved, active and passive components, the transceiver design, and multiple propagation parameters and other parameters as well. Thank you so much, sir, for the introduction. Next, we have with us Dr. Arvind Kumar, sir. Dr. Arvind Kumar currently serves as an assistant professor in the Department of Electronics and Communication Engineering at VNIT Nagpur. Prior to this, he held a faculty position at VIT, Bangalore from 2020 to 2022. He earned his PhD in Microwave and RF Engineering from the National Institute of Technology, Trichy in 2019. He was awarded the prestigious Young Faculty Research Fellowship by the Ministry of Electronics and Information Technology, Government of India in 2025, and received the Young Professionals Excellence Award from WMS Society and IEEE-APS and IIIT-DM Kachikaram in the same year. His research excellence has earned him global recognition as one of Stanford University's top 2% scientists in the world for 5 consecutive years from 2021 to 2025. In 2024, he was honored with the Scientific High-Level Visiting Fellowship by the Government of France, allowing him to undertake a short-term research stay at the University of Physics, IUTI. We welcome you, sir. I request our head of the department, Dr. Jayakant ma'am, to visit Dr. Arvind Kumar. Thank you so much, ma'am. I request sir to carry forward with the session.
Okay, good afternoon to everyone. Am I audible? Yes. Okay, fine. So initially I will give introduction to transistor design, how we can design mathematically and exactly what we need in transistor. And then using AWR, little demonstration we will give with the help of MTech Scholar is available. So first of all, I will ask, do you know fundamentals of amplifier? Can you design amplifier? Or is there any difference between the traditionally low frequency, what amplifier we are designing, and how we can design amplifier at voice change? Okay. I think without that also I am audible in my class of 120. I never use in my class mic, so my voice is loud enough. Okay, fine. Okay, otherwise back people can come in front. Okay, fine. So here I am going to introduce amplifier design specifically at higher frequency. Higher frequency means, as Professor Gandhi sir said, we are talking about 1 to 10 gigahertz. So in that range, how we can start designing of the amplifier? To start designing of amplifier, we need transistor, right? But transistor is not only a thing what we are studying. It's going to amplify the signal, but many things required. What we know fundamentally, small signal analysis, then large signal analysis, and all those things. But apart from that, when we talk about very high frequency amplifier, we need many things. Specifically, specifications are again different for particular transistor. Like we will talk about more about the S parameters. So we will study transistor by assuming it's a two-port network. While we were studying at the EDC transistor design or transistors analysis, during that time we have studied H parameter, or using ABCD parameter we have done analysis. But at the micro frequency or very high frequency, it's very difficult to attain exact value of current and voltages, because signal is in the air, so it's very difficult to calculate exact value of what is value of current, what is value of the voltage. So rather than we are adopting another analogy or another type of theory, that is what we call transmission line theory, or here we are going to deal the network with the help of the S parameters. So S parameter are just analogous, or it's similar to ABCD parameter or hybrid parameter like S parameters only. But with help of that, we are just trying to find out how much power we are sending and how much we are getting it back. That sort of analysis we are going to do. And whatever transistor we are going to purchase from the market, its specification will be given in the terms of the S parameters. So I will start from there, how we assume exactly transistor, and then what type of analysis we can do, and then how we can get desired gain. Okay, this introduction already given, but my research interest is not power amplifier or like such. It's a little different. I'm antenna guy. I do work on substrate integrated waveguide based antennas. I contributed around 50 journals in this particular topic only. Apart from that, millimeter waves also I do work, and this is just little research portfolio. So just I am doing little my publicity. Okay, so I do have one vacancy for JRF. If you are interested, you can join. This is my research profile, and currently few projects are undergoing by various funding agencies. One recently I got research grant from IEEE APS Society. Apart from that, I have one funded project of DRDO. So there I am looking for some JRF project associated without gate. And then electromagnetic knee imaging system, I have funding from MIT. Then FIST as a coordinator, as a whole department, we got this FIST. So where I am coordinating all those activities. Apart from that, few other projects are there like filtering antenna or fluid antenna. So different funding agencies, as you can see here, these are supporting me as of now. We have very well established facilities in our department. Initiated by Professor Gandhi sir only. We have brand new anechoic chamber, few fabrication facilities, SPR, spectrum analyzer, and many other things. Here you can see photo. So with MTech guys, this brand newly built anechoic chamber we have. If you wish, you can do measurement there in collaboration with BNIT. Apart from that, we are going to extend our facility up to 110 gigahertz by using SDR or the new vector network analyzer we are going to purchase, or it's just like under procurement. So that kind of experiment setup for upcoming future generation communication like 6G and all those things, we are going to do analysis. Here you can see VDA based model, and those are just proposed things as of now, but we got funding from FIST 1.43 crore. So in that it's under procurement. Okay. Apart from that, here many faculty are available from different colleges. So I have a very good option if you wish to work with us or with our group, RF group at VNIT. We offer internship during summer vacation. So I got funding from IEEE around 4800 USD. So I have given proposal to them. I am going to hire or I'm going to invite 4 to 5 students from one college surrounding or around BNIT, so that the students can come and they can do internship, specifically third year, specifically in areas of RF and micro engineering and antenna design. And if someone is interested in circuit level design, they can contact Gandhi sir. And apart from that, we will teach these softwares and hands-on, and finally, more would be like research publication or some contribution. These are the things, and one research associate opening is there under this project. So this much is enough. Yeah. So now I'm coming here. So this you have seen the inverting amplifier, where gain bandwidth product remain constant. But if you look, very interesting phenomenon around gain bandwidth product or frequency versus gain bandwidth ratio. If you are moving towards the high frequency, your gain is going to decline. And if you look at the gain formula of this inverting amplifier, it's something negation of R2, that is feedback resistance over this input resistance. And then again, if you look here, you have ample options. What value of R1 and R2 you can choose. Accordingly, gain can be adjusted. So let us assume if you want 1000 gain, so you can take any of this ratio, everything is going to fulfill your requirement. But there is, or there could be different type of trade-off. If you are choosing, for example, this one, you are going to get gain around 10 raised to power 3, which is around over here. We are talking about here, not at very high frequency where it's going to reduce, or in middle if you are talking 10 raised to power 3, if you want to gain bandwidth product, you have these options. But which one to choose? And what would be your criteria, or what you can choose? Can anybody tell me? Which one is better option? So fortunately, I was working at DIT Vano. She was a student there, doctoral student. Okay, so if you choose, for example, 1 ohm over here, your gain bandwidth requirement is going to fulfill. It's a very good option. But if you are using very small resistance or input impedance at the input side, it's very bad idea. It's going to choose high amount of noise at the initial stage, and your system noise figure and other things are going to get disturbed, right? So inherently, if you take this open circuit, its input impedance is around 1 mega ohm, right? Very high. So that thing you are going to deal, or you are going to compensate over here. So, and if you are taking very high over here and output impedance you are taking high, then again unwanted wastage of power and all those things. So such constraints are there. What to choose? So now slowly I will come to point how you can take decision for such problem. Apart from that, I can tell from where I have taken those slides and reference. Initially, you might have seen this is book suggested by Gandhi sir only, and then few lecture videos of Professor Girish Kumar from IIT Bombay. So I have taken from there. You can search after that and you can see. Yes. So let us assume now you want to design one amplifier using some transistor. When you look into transistor, or you going for market, let's say at 2 gigahertz, you want to design some amplifier, some specifications will be given. Specification means how to bias or how much biasing things you can give. Apart from that, some parameters will be given in the terms of the S parameters. S parameter represents, like S11 is there, when you are feeding at the port 1, how much reflection you are getting at port 1 again. For example, you are feeding this one from here, so it's not necessary 100% power will flow. Some reflection will come back. So this is the thing which is going to give ratio how much you want to insert and how much you are getting back, and vice versa. So accordingly, this parameter will be there. And S21 parameter, how much input power you are giving at the port 1 and how much you are getting at port 2. So while you are sending something from here and getting it over here, it's not necessary every time you are going to get 100%. Reason is something terminology we call isolation loss, insertion loss. Insertion loss means, for example, if I'm moving from here to there, some sort of energy I will lose. What energy I have right now, I want to maintain up to that point. So similarly, when microwave signal travels from the port 1 to port 2, whatever in between happening, some losses will happen. So this prominently very important in the terms of filter, but here that parameter we have to maintain, or very minimal losses should be there. So we want to maintain this one as minimal as possible, because reflection should occur minimum when you are inserting from the port, because if I want to send signal, it shouldn't come back towards me, it should go forward, right? So this parameter usually I need to see. Apart from that, how much I want to send path, this parameter also I need to see. So over the frequency, if I see response, power flowing mechanism at DC is very good over here. You are getting very pretty good gain. This is the gain curve, and this is the frequency. And as I increase frequency, power flow or signal going from the port 1 to port 2, its strength is going to reduce, that is gain is reducing. And here if you see, at the lower frequency, mismatch is more, this reflection is more, right? So somewhere you have to trade off where more things you are getting better, and from that point you need to start designing, or your transistor is going to operate at that point pretty good. So that kind of knowledge will be given. I will share slides with you. Those are MTech curriculum only. So if you wish, I will share. So if you are looking over here, reflection is minimal over here. So if you want to design transistors, it's going to fulfill your requirement better over here. So these are things will be given on your data sheet. And other things you can see from here, these and many information will be given. But it's pretty important, you have to understand S parameters, why it's critically important. It's you will understand in upcoming slide. Transistor you can see as a two-port network. How? Because at one side you are feeding something, you are getting something at the other side. That means you are feeding small signal over here. This is, let's say, transistor. You are feeding something from here, and you are getting something over here. For example, you are feeding this as a small signal, you are going to get quite improved version of the signal, assuming CE configuration. You're going to get like that. So it's going to enhance your energy. How it's going to enhance? Because you are providing some sort of energy by using biasing network. So that battery energy gets converted into, and it's going to increase whatever that mechanism is there, transistor action, that everybody knows. So same phenomenon is going to happen. But in order to analyze the transistor at high frequency, we are going to take help of the S parameter. So we can take this one as an input port and this one as an output port. If you are assuming input and output port at the high frequency, we are going to deal with the reflected wave and the incident wave. कुछ वेव वापस आ गई हमारे पास और कुछ अंदर चली गई, ठीक है? So in that way you can define S parameter, this is scattering parameter. So whichever wave is falling or incidenting, that by convention we are representing by A parameter or A1 or A2, and this is reflecting back, that we can represent with alpha of B. So this is conventionally representing like that. Based on that, we can define another parameter, what we call reflection coefficient. So if this wave is incidenting over here, some portion is going to reflect it back. So we can define input parameter or gamma in reflection coefficient at input side when you are looking this circuit from this side. Okay, if you are looking this circuit from this side towards the source, then your meaning is going to change. So wherever ratio you are taking by B1 over A1, that is going to change A1 over B1 and so on. So likewise, you have to manipulate according to your understanding. So here we again define the incident wave is A1, and going back or forward moving wave represented by B2, and this is incidenting from this direction. If you are looking from this direction. So when you are defining this gamma L, it's going to be reverse. How you are defined over here. So here simple definition is gamma L is written over here, A2 over B2. A is reflected wave. You can see here, if you are looking from this end, here we are looking gamma L reflection coefficient towards the load side, so we are looking like this. So what incident wave incidenting on this one, that will be going to act as a reflected wave over here. So you have defined gamma L and using gamma L and other by doing some manipulation or by solving equation number 1 and 2, utilizing this concept over here and inserting in equation number 4, you are going to get gamma in value something like this in the terms of S parameters. So here I will just say, you just try to understand what is meaning of S formula. When you are putting input power at the port 1, how much going to reflect back towards the input 1, and how much power is coming back from port 2 to port 1. That ideally should be 0, right? Because you want to send signal from here, it should come back. But there is nothing like ideal, so we have shown over here as per calculation over here. If nothing is coming, this component going to be 0. So from here, what you are getting, gamma in input reflection coefficient should be equal to S11 parameters, and S11 parameter is quantity which manufacturers are going to provide you. Okay, so you are going to relate this one. Why I am telling all those things? Because ultimately you are going to design amplifier, and amplifier means you want some sort of gain, and gain is going to depend how much power can go inside the transistor, and that thing is going to depend upon all those parameters. Fine. So here it further gets solved. Gamma in something you define like this, and this delta you have assumed that is just this S matrix what you are seeing, it's a determinant. Okay, so this delta is determinant of this matrix, and gamma in you got in this way. So similarly, if you are looking this network from this end, you can calculate this gamma n also. By symmetry, you can say here S22 will come, this portion is going to remain same. Here in will come, and here S11 will come. You can solve it. Okay, so I am showing directly over here. Okay, this is what you got. Okay, gamma output. So gamma output, how I am seeing? I am seeing again from this end. Okay, I am talking about transistor only. Initially, when I sending signal from here, I talked about load. But here I am not talking about load because I am seeing gamma output, how much it would be. If ideally, if I want to match, it should be equal to this portion. Because they shouldn't be. And finally, gamma out formula, you got this one. Okay, so far we have used S matrix, or we have represented the transistor two-port network, and which we represented by one S matrix, 2 cross 2 matrix, and the subscript what you are seeing, those are going to represent power relation or how power is flowing. Okay, based on that, we have calculated few quantities, which is gamma out and gamma in. Fine. How much this transistor can give us gain? Ultimately, we want to calculate gain. That is gamma out, gamma in. That is not our goal. We have nothing to do with gamma in and gamma out. Ultimately, we want to calculate how much transistor can give us gain, right? So, simplify, or in order to understand gain mechanism, we are using control system match and gain formula, and we can convert this one into signal flow graph, and we can calculate its gain value. Assuming that how much power flowing from the BS, that means how much power coming out through the source. So how much we are getting over here, if we are taking ratio of V2 over Vs, that is ultimately going to give us gain. So using this signal flow graph, we can calculate gain. You might forget formula, but everything is given over here. With the help of that, you can calculate. How we are calculating? It was the ratio of how much direct paths are there divided by 1 minus coupling of loops, then minus single pair of loops, then non-touching loop multiplication, and all those things were there. If you look at this formula, you are going to recollect BTech third year control system. Hopefully, you are remembering this transfer function formula. So this transfer function formula I have applied in this signal flow graph. It's very simple, not difficult like BTech numerical. Easily one can perceive that only one path to which BS to B2 you can reach. That is S21, and this is a one loop, this is another loop, this is a third loop. So 3 loops are there, 2 loops are non-touching, this is non-touching, in between one loop is there, so this one and this one are 2 non-touching loops. So accordingly, we can fit in this formula. So path 1 multiplied by 1 minus and all those paths So although those are not existing. So here you can have this terminology and this terminology only. So if you put all those values over here, you are going to get total gain of this particular setup what you made by using 2 cross 2 matrix, you are going to get into over Bs, and this is your gain of your transistor. Now look into this carefully. On what thing gain is going to depend. One is S parameter. From where you will get S parameter? Manufacturer itself will give S parameters. S11, S21. You have to understand what is S11, what is S22, what is S21, what is S12, and so on. By knowing this, these values are given, but what you don't have gamma L, which we previously you have calculated. And here some gamma S and all those terminologies are there. So slowly we will convert all those parameters what we are knowing. थोड़ा मैथ्स ज्यादा तो नहीं हो रहा? नहीं, ज्यादा हो रहा है। But इसके बिना ट्रांजिस्टर एम्पलीफायर डिजाइन होता नहीं। You have to know terminology, otherwise you will never understand why you are doing. Okay. So to design amplifier, we are going to define some sort of gains. There are 3 types of gains. Usually Gandhi sir teach in his class. Here I copying his things. One is transducer gain that generally we are representing with GT. Another is available power gain. Number 3 is operating power gain. And all having different meanings like P in wherever you are seeing that is input power, PL is power delivered to the load. Exactly how much power is going towards the load. Power available from the source represented by power ABS, and power available in network means transistor में कितनी power available है. And these are different type of gains. So transducer gain is just the ratio of power delivered to the load divided by power available in the source. Likewise, available power gain, that is power available in network, जितनी network में available होगी उतनी power आप ले पाओगे ना, divided by power available from the source. And then operating power gain represented by power delivered to the load divided by how much input power was there, or initially how much power you had. Okay, or from where we are leaving source and from other end we are looking for gamma in, so we are dealing over here that sort of power. So these are the terminology which is going to give us gain of the transistor. So before starting, we should know these terminology, and after that we can start the calculation of the gain. By knowing previous things, from here you can understand how you can calculate transducer gain. So transducer gain was nothing but the ratio of the PL over power available from the source, and you can calculate with the help of these coefficient, or you can say how much magnitude you have. You can make it half, and the V square over 2R, R is 1 over here, same formula we are using over here, otherwise amplitude is square divided by 2. So how you are remembering, it's up to you. So that ratio has been taken over here, and this is what we got finally, transducer gain. I'm not going one by one how we solve maths, you can see, and finally you are going to get very organized formula, this one. If you look into this formula, you forget this one and forget this one. What is this? This is the path from port 1 to port 2, square of that one. And if you look this side, this complete quantity represents input side of the transistor. Port 1, port from this side, and this quantity represents towards the output side, load side, or you can say gamma out. So this is going to deal with gamma in, or S11. This is going to deal with gamma out, or the S22 parameters. So it's surrounded by this one. Now, initially when we were trying to calculate gain, it ideally should depend upon this path only, but it depending on these factors. That means how many things you are making towards the input side and output side, your gain of the transistor is going to depend upon those parameters as well. So how much you are expecting, these fellow can degrade your gain performance. So you have to deal very carefully with these parameters. I will let you know how we can deal with that type of parameters. Before that, transducer gain, we can further classify or you can find out the three cases of amplifier gain. Number one is mass transducer power gain, which we represent by TM usually. Mass means something is masked. It doesn't mean that reflection is not there, but few things are masked. Mask means maximum power transfer theorem we are adopting. So when we are adopting maximum power transfer theorem, it doesn't mean 100% efficiency और पूरी 100% पावर चलेगी इसका मतलब ये नहीं होता है. So something we are doing like that. So if reflection coefficient at the source side is 0 and reflection coefficient at the load side 0, then you are going to get this condition. GTUM, which is S21 square. Otherwise, in other case, if you adopt the power flow from the port 2 to port 1, if there is no reverse flow, then you can consider unilateral transducer gain, GTU. That means your transistor you have made in such a way power is flowing only forward direction, nothing is coming back. Okay, so that you can make it 0. So previously what we have defined over there, by sorting or by solving that one, GTU you are going to get this one. How much maximum gain you can get by using above equation? What would be the maximum gain? As I said, if this component completely match, this will be conjugate of this one. It will match the condition, so this will be square of this one. So one portion will get cancelled out with this, you are going to get only this one. Similarly, here S22 parameter at the port from port 2 to port 2 reflection would be exactly complex conjugate of reflection coefficient at the load side. During that time, this will be square of this one, and this one you can cancel it out. Hopefully it's clear. What I am trying to say is, the maximum unilateral transducer gain would be possible only at the input side if you are assuming gamma S would be equal to complex conjugate of S11. So if you are putting this value over here, you are going to get this one, and S22 की जगह अगर ये put कर दोगे इसका complex conjugate, आपके पास ये sort out होके आ जाएगा. Why I am doing this one? What is need or why every step we are going? Exactly, sometimes when you are designing transistor, for example, you want 10 dB gain. Okay, but before designing some amplifier at 10 dB gain, you must know how much maximum gain your transistor can give. आपके पास कुछ ऐसा ट्रांजिस्टर उसका मैक्सिमम गेन ही 5 dB आ रहा है, आप 10 dB का कहां से बना लोगे, राइट? So you have to find out how much maximum gain can give. After that, you can start designing. Otherwise, if you do not know how much maximum gain you want, then how you will purchase some transistor from market? When you are going to market, if I want 20 dB gain, I want to purchase, or I have to have that type of transistor which can give me 20 dB gain, right? Somebody want 5 dB gain, उसकी किसी की requirement कुछ इतनी हो सकती है, तो वैसे वाला ट्रांजिस्टर करेगा. तो मुझे पता होना चाहिए how much exactly gain I want or how much maximum gain my transistor can give. That thing should be clear. Okay, why I am saying this one? From many point of view, this terminology is very important. Sometimes what happens, your transistor is giving 10 dB gain and you want 9.7 dB gain. So if you are purchasing this transistor, your requirement is going to fulfill. But if some error happened, let's say 5 dB, some tolerance happened, then 5 dB tolerance means let's say 0.5 dB, so it will go 10.3, right? 10.2. Some due to some tolerance. So you are going to face some sort of problem. Okay, और वो अगर क्या उससे माइनस हो गया टॉलरेंस प्लस माइनस 0.5 dB अगर टॉलरेंस है, then your this requirement is not going to fulfill. Okay, अगर टॉलरेंस अगर वैसा है तो और otherwise in EDC what we are studying, your transistor may go into saturation mode or cut off mode, तो आपका क्लिप हो जाता है ऊपर वाली वैसे वाली प्रॉब्लम्स आ सकती है. So that's why we have defined these two terminology कि maximum gain कितना दे सकता है और practically कितना दे सकता है जो ऊपर वाला है. अगर मैच कंडीशन सब कुछ आपने बढ़िया से मैच किया, प्रैक्टिकल इतना दे सकता है, मैक्सिमम इतना दे सकता है. By assuming or taking ratio of this one and this terminology, we can add one more thing: how much your transistor can give error, and that is what we can call tolerance. What I am defining over here. So that is the reason why I have defined these terminologies. Apart from that, before starting, you have to check few conditions whether your transistor is stable or not. Stable or not means what? Because load line concept याद होगा ना आपको? It was something like this. This is the gain of transistor and this was load line. So your transistor should operate somewhere, something like this, right? This is over here. You want to keep nearby this region or after this cutoff region. You want to keep this one in middle of that. Load line is giving that idea. Your transistor should go towards the saturation or cutoff. इसका ऑपरेटिंग पॉइंट मिडिल में होना चाहिए, थोड़ा बहुत इधर उधर भी हो गया तो भी आपको सस्टेन कंडीशन रहे और गेन मिल जाए. That is what exactly you want, right? So looking similar type of thing, we need to see one important parameter whether your transistor is stable or not. Okay, so to check the stability of the transistor, two things we are going to change. Check. Number one is stability factor, and number two is this delta. So this condition we have to check. We have to calculate K with the help of this delta, that is determinant of S matrix of 2 plus 2 S parameter, and putting this one we are going to get some value of the K. If you are getting the value of the K something like this, delta आपका 1 से कम है और K 1 से greater है, your transistor will be unconditionally always stable. Otherwise, if this condition is not satisfied, your transistor will be unstable. We don't call unstable. We will find condition where it could be stable, and we will eliminate that type of region. Fine. Apart from that, for bilateral case, S21 power may flow from the port 1 to port 2, so that won't be 0. So in that case only we need to check the stability criteria. ऐसा जरूरी नहीं है कि थोड़ा सा रिफ्लेक्शन की वजह से वापस भी पार आती है. Microwave power flow towards the reverse direction if you are using even isolator, then also that thing may happen. So during that time we have to check this condition. If case number 1 is satisfied, then transistor will be always stable. Means if there is no flow of the power from port 2 to port 1, then you can assume the condition 1 and it would be always stable. To find this type of situation or to find conditionally stable criteria, same equation what we have for gamma out and gamma in, we have solved little bit more as per given book or few lectures available online. After that, you will find that you will get some sort of equation like this. And this equation, if you look at carefully, it resembling some sort of circles. आप जो लाइन की इक्वेशन आती थी और उसमें अगर ट्रांसफॉर्म करते हो and remembering 10th standard basic, you can transform this equation into circle, and with the help of that you can find out circles radius and circles center. So by using this equation we have calculated some circles center and some circles radius. Okay, once you calculate this, you take help of the Smith chart and draw that circle. This one is done towards the input side, and similarly circle equation you can find towards the output side. So few circles we can draw, and with the help of those circles you can find out the stability, or you can clip out that portion. We are not understanding so much, so we can take one example and we can understand design of the amplifier. Let us say this is the problem given. So while you are starting or doing hands-on, such problem will be given. So you have to start with some transistor at the 800 megahertz is given, and these parameters are given by manufacturer. So point number 1 is you just check whether transistor is stable or not. Stability you have to check. So you have checked stability and you found that these values, this one you are getting less than 1 and this one you are getting not greater than 1. That means transistor is not stable. This is supposed to be greater than 1, right? Okay. So transistor is not stable. So if it is not stable, we will not throw the transistor. We will find out where it could be stable. So now we will take help of the circle equation what I showed in previous slide, the circle equation, and I will try to plot same thing on the Smith chart. Okay, how I will plot? If you look this Smith chart, from here to here, I will take magnitude as a 1. Okay, and I have calculated the center CS and RS. This is the center of the circle lying over here, and this is the radius. So this is what I have calculated, and some angle is given over here. So by using compass, I have taken the angle from here to here 122, and just made the arc. If from here to here, let's say if 1 meter, so 1 मीटर अगर इतना है तो 1.04 meter will be coming out of this one, and from here taking that same radius you can draw a circle and you will find some portion is clipping over here. Similarly at load side also you can do. Not understanding. It's a bit tricky, you have to spend a lot of time.
I think whatever you cover in multiple lectures, you are covering this short duration.
Otherwise, transistor design is not an easy joke. Sorry, amplifier design you cannot.
Means am I correct? Means is my observation correct?
This usually I teach in 7-8 lectures.
Concentrated dose, okay. But because they are familiar, so you can.
All are teachers, no? So they know transistor. I need not to tell how transistor works. So आपको फिर से समझा देता हूँ. देखो, CS, what you are getting, CS, this is the center, this is the radius. Okay. So हमको एक ऐसा सर्कल ड्रॉ करना है जिसका सेंटर इतना यहाँ पर हो और उसकी रेडियस ये है. That we are talking from the input side, source side. So what I have done, 1.79 is its center at the distance of 1.79, and this angle is 122. So to do or to draw this on a Smith chart, you just take a Smith chart and locate its center. This is the Smith chart center. Okay. And then you just locate where is its center. So center information is given by 1.79 and angle is 122. So you just make angle 122 over here, or it's given here also angular line. Just draw a very big line over here. That's all. Okay, so this one angle you have drawn. Now next step is you just mark where is 1.79. Next step. I said from this point to this point just assume 1 meter, or let us say 1 unit. And this is 1.79 unit. Okay, so ये almost इसका double हो जाएगा. यहाँ ऐसे assume करो कि ये यहाँ से लेके यहाँ तक 100 मीटर है और आपको 179 मीटर कितना होगा वो कैलकुलेट करना है. So आप क्या कर सकते हो, पहले 1.100 मीटर यहाँ तक हो गया, उसके बाद 79 मीटर मार्क करना है. तो कंपास की हेल्प से आप यहाँ पर एक आर्क लगा दीजिए, ये सेंटर लेते हो. Okay, so you got CS, right? Once you got CS means you got center of that particular circle. After that, radius information is given over here. That is 1.04. So initially you assumed 100, so this is 104. So 104 means you take over here as a center compass and take radius of 104. Assuming that this is 100, now 104 will be itna, right? So you will make one circle over here. So you will find that some portion of the Smith chart clipping over here. That portion is called unstable region. अगर आपका reflection coefficient अभी कहीं पर नहीं है यहाँ पर, except this portion आपका transistor stable रहेगा. That means I just eliminated the information where transistor was going towards the saturation or cutoff region. So if you are not opting your reflection coefficient over here, Smith chart represent reflection coefficient and number of combination. यहाँ पर कुछ reflection होगा, कुछ यहाँ पर होगा, कुछ यहाँ पर होगा, जो gamma L और gamma S आप करें. Similarly, same thing we can do towards the output side, load side. So वैसे का वैसे ये angle बना हुआ, और फिर यहाँ से वापस आर्क से काट दीजिए. So you shouldn't keep your reflection coefficient over here. Now one may ask which is the most unstable region over in this Smith chart. Which is most unstable region? This one, this one, this one, this one. This one, right? Because आपको अंदर की तरफ आना है, यहाँ से अंदर आने के लिए सबसे ज्यादा मशक्कत करनी पड़ेगी, तो ये सबसे ज्यादा अनस्टेबल है. This is just a border line, which is most or which is favorable point, nearest point ये वाला है, because which point is nearer to the center, that is called matched point. So you are always looking for the point which is nearest to the center. So you are looking for this point. So this is nearest one. This will be relatively stable. Okay. Similarly, this is at the output side. So what you got from here is you just made the transistor conditionally stable rather than making it unstable. Okay. So these are the reasons which represent unstable region. Is it okay? Shall I move next? Okay. Here, GTU, transducer gain unilateral, and maximum value of the gain is given over here. So from this formula you can note down this component represent input side, this component represent output side, and this is a forward path. And this same formula is going to give me maximum value of the gain at the input side. This is going to give me maximum value of the gain at the output side. And total gain is just a combination of all those things. So how much gain you want? For example, one transistor can maximum, it can give gain of 20 dB, but आपको 11 ही चाहिए, तो आप 20 वाले gain के लिए क्यों transistor बनाओगे? So you have flexibility, you can play with these parameters, and accordingly you can design. But maximum value you can get according to this formula only. Okay. So why I am showing this one? I will just try to find out how much maximum error my transistor can give. Means how much tolerances I can get from the particular transistor. Okay, before that, I will show another thing. By using those equations, again you can convert it to circles, and constant gain circle also you can get. Means कितना reflection coefficient आपका होगा कि ये constant gain मिलता रहेगा. Transistor sometimes may fluctuate, right? Gain up and down. आपने mic का देखा होगा. कभी एकदम आवाज बढ़ती है, कभी घटती है. So that means your amplifier is not stable during that time, or it's not providing constant gain. Sometimes voice बिल्कुल कम हो जाता है, कभी ज़्यादा बढ़ जाता है. Then that sort of problems you are going to get. That means constant gain circles you are looking for, or you have to calculate constant gain capability, और कितना reflection coefficient होगा कि वो constant gain आपको दे सके. Fine. So these are just circles similar to previous case. I won't go into detail. So I will show just by example. Just skipping this one. Apart from that, using maximum gain criteria and unilateral transducer gain, you can find out the error, how much error you can get in this gain criteria, assuming that how GTU maximum you can get and how much transducer gain you are getting. Based on that, you are going to get some error. So आपको हरदम इतना tolerance लेके चलना पड़ेगा. Every time you have to calculate, for example, m की value अगर 2 आती है और आपको maximum gain का transistor, let's say your transistor can give 10 dB maximum gain, and you want to design some amplifier whose gain you want 9 dB, and इसकी value अगर 2 dB आ जाती है, then tolerance limit will go out. Right? What I am trying to say is, you want some transistor that maximum gain value can be 10 dB, and you want to design for 9 dB. Okay? And that M factor, that error factor is coming, let's say, 2 dB. Right? So अगर कुछ गलती हुई उसमें और कुछ मैनिपुलेशन वोल्टेज और करंट का हुआ, तो मैक्सिमम गेन 12 dB पहुंच सकता है. ये प्लस माइनस स्वैप में हो सकता है, and then it may go 8 dB, but you want 9 dB, right? So during this condition will be okay, but here the maximum gain you can get 8 dB during minus 2 dB. Okay, what I am trying to say is, tolerance limit always you have to take into consideration. If you are designing some amplifier who can give gain of 10 dB maximum, and you want to design for 9 dB, and tolerance you are assuming, let's say 2 dB, plus minus 2 dB. So your gain may vary from 12 dB to 8 dB, or reverse I can say. Right, but you want this one. But if tolerance is coming in this limit, that problem is going to fail. So every time before starting design, you have to check M also. आपका ट्रांजिस्टर मैक्सिमम कितना गेन दे रहा है, आपको कितना के लिए कितने के लिए डिजाइन करना है, and then how much tolerance. So with this value you have to do. Usually M for given parameters we are getting around this one. 2 dB तक नहीं आता. We are going to get, but you have to take into consideration many times. Okay. Okay, let's say some transistor now you want to design and these are parameters are given. This same example you can do hands-on. So you can look into this problem once again. What is given? Some S parameters are given. Gallium arsenide MOSFET is given at 8 GHz frequency, and these S parameters are given in the terms of magnitude and angle. Okay, and you want to design some amplifier at 10 dB. So from where you are going to start? सबसे पहले क्या देखो? Number one step, as I told, you need to check whether your transistor is stable or not. So K and delta you need to calculate. So you have checked over here stability. You have calculated delta, you have calculated K. So fortunately you got this is less than 1 and this is greater than 1. That means transistor is stable. You need not to draw those circles, whether it is stable or not. So transistor is stable, you can start your design. Fine. So after that, once you design this one, I want to check it whether how much maximum gain my transistor can give. That condition I have to check. So I have calculated over here GTU max, how much maximum gain I can get. And you observe that you got maximum gain 10.67 dB. Okay, so I want 10 and the maximum giving 10.67. But same time you have to realize if tolerance is more than 7.7, then somewhere your transistor is going to create problem. So you have to calculate M factor also, which error limit is also given, right? So this one you calculated different value. You are designing over here. You have found unconditionally stable, and GM transducer matched gain also you have calculated. This is you are getting this much. That means what is this parameter? S21 square. S21 whole square. Okay. Maximum gain वाला फॉर्मूला याद है ना? एक साइड में इनपुट साइड, दूसरी साइड में आउटपुट साइड, एंड ये इसका स्क्वायर. तो ये वाला कंपोनेंट यहाँ पर आ गया. And total gain you are getting this much. This is maximum value. So this one analysis you have done. एक बार देख लीजिए को समझ में नहीं आया. ये तो समझ में आ जाना चाहिए, कोई दिक्कत नहीं. See, we are going to design one amplifier whose gain we want 10 dB. Okay, so step number one, we have checked its stability. We found that transistor is stable. So we need not to go for that reason which is clipping off or going towards the saturation or going towards the cutoff. That problem gets sorted out. We need not to check. Next step, we need to check how much maximum gain my transistor can give. That is what I want to check. So my maximum gain I can get this much. Okay. And when signal is going from the port 1 to port 2, how much gain I can get? That I can get very easily by squaring this component. And that same thing I have calculated over here. Okay, this much calculation I have done. That one I can utilize for calculating reflection coefficient and all those things. Okay, so next is maximum error, how much I can get. So simply as a designer, you just open book and put values into the formula. So here I got maximum tolerance limit is this much, and it was giving me 10.67, so my requirement is going to be. So this is what? This is tolerance limit. If I put, you put all those values over here, you are going to get tolerance limit is this value. So अगर आप माइनस करते हो 0.67 से तो भी यहाँ पर हो रहा है उसमें ऐड कर दो कोई दिक्कत नहीं. Then things are going to satisfy. Fine. Now understand here what exactly happening over here, or how you can solve. This is the maximum gain which transistor can give. This is a gain component which you are getting from input side. This is gain component which you are getting from output side, and maximum gain you are getting this one. और आपको डिजाइन कितने के लिए करना है? 10 के लिए. तो आप क्या कर सकते हो? Initially what you can do, you can equate these values to 10 dB and एक को assume कर लो इसको, और इससे कम भी assume कर सकते हो क्योंकि इनपुट साइड में मैक्सिमम गेन इतना हो सकता है, आउटपुट साइड का मैक्सिमम गेन इतना है, और फॉरवर्ड पाथ का इतना है, और इन टोटल का मल्टीप्लिकेशन इतना आ रहा है, और आपको इस तरीके से इन कंपोनेंट को सेट करना है कि इनका मल्टीप्लिकेशन आपके 10 के बराबर आ जाए. Okay, so designers exercise starts from here. So what you can do, this component maximum you have this much, so minimum I can have 1 2 3 4 कुछ भी हो सकता है. तो आप इसको कुछ assume कर लीजिए. Let's say I am taking 1.5 1.25. So then if you put into this equation, you can get this component ZL. और इस कंपोनेंट को कैलकुलेट कर सकते हो, और ये कंपोनेंट आपके पास स्टैंडर्ड है, तो आप फिर इसको एंड इसको और इसको मल्टीप्लाई करोगे तो आपके पास 10 आ जाएगा. राइट. सो हियर लिटिल एक्सरसाइज स्टार्ट्स एंड पुटिंग दिस इनटू दीस फॉर्मूलाज. समबडी वांट, सर मैं 1.8 चूज कर लूं क्या? यू कैन डू. मैं 1 चूज कर लूं क्या? आप वो भी कर सकते हो. यू कैन चूज एनी वैल्यू until unless your conditions are satisfied. So it's depending upon the designer how much you want to choose and how accordingly things are going to be solved. Okay, calculate. Now I want to see how gain of my transistor is going to vary. So by using the circle equation, you can draw again circles by using radius and the center of the circle. So let us assume this is, you are getting constant gain circle towards the source side. This is constant circles information towards the load side. By using this, what you can do, you can draw again on the Smith chart. So by using those these information towards the source side, towards the load side, I have drawn on the Smith chart, and I found that if I moving on this circle, all reflection coefficient whatever available, my gain is remaining constant. So you can take any value of reflection coefficient. आप 0.7 ले लो, 0.8 ले लो, 0.3 ले लो, कितनी भी ले लो. But designer always think which is best or optimal value. And as I said, the point which is nearer to center, that is called match point. And at that point you will get maximum power transfer. और maximum power transfer theorem जो है वहाँ पर अच्छे से satisfy होती है, and there you are going to get or that point will called optimal point. So this is my center point. So this point will be optimal point always. So you have to choose this reflection coefficient. So initially what we have studied, gamma L and gamma S. मैंने कहीं आपको ये नहीं बताया उसकी वैल्यू क्या है, कितनी लेनी है, कैसे लेनी है. You can get it directly from here, Smith chart. और gamma L यहाँ से आ जाएगा. That is how you are going to calculate gamma L and gamma S. ये यहाँ पर जितना मैग्नीट्यूड है और ये नीचे स्केल होती है इसकी, वहाँ से सीधा आप कैलकुलेट कर सकते हो. आपको ऐसे कैलकुलेट नहीं करना आता है तो आप क्या करो, इसको एज्यूम करो पूरी को 1. ठीक है, पूरी को 1 एज्यूम किया तो हाफ कितना होगा, 0.5 होगा. ये इतना लेंथ कितना होगा, 0.25 होगा. तो अगर रिफ्लेक्शन कोएफिशिएंट इतनी रेडियस वाला है, यहाँ से लेके इतनी रेडियस उसकी आ रही है 0.25, तो 0.25 रिफ्लेक्शन कोएफिशिएंट हो गया. अगर ये उसकी रेडियस इतनी आ रही है, लेट्स अज्यूम करो 0.1, तो रिफ्लेक्शन कोएफिशिएंट 0.1 हो गया यहाँ पे. So easily without using calculator or anything, you can by visual observation, gamma जो इतना कॉम्प्लेक्स लग रहा था कि कैसे सॉल्व होगा और इतनी सारी इक्वेशंस आपको जो दिखाई, वो अगर वो सारी चीजें समझ में आ गई तो कहाँ चला गया, so you can calculate very easily. Okay, so अब रिफ्लेक्शन कोएफिशिएंट किस में आपने देखा था, गामा एल, यू हैव सीन द गेन फार्मूला, सो वहां पर ये वाली वैल्यू पुट कर दो और आउटपुट साइड में ये वाली वैल्यू पुट कर दो, आपका 10 dB गेन आ जाएगा. राइट नाउ रिफ्लेक्शन कोएफिशिएंट और that was gamma. If you want, then you have to design matching circuit towards the input side and towards the output side. 100% power transfer तभी होती है when things are get matched, but many times reflection will occur. But you do not want reflection more than this. If you want reflection more than this coefficient, then what will happen? You will not get your desired gain. So exactly you want that much. For that purpose, you need to design impedance matching circuit towards the output side and towards the input side. So impedance matching, if you have little knowledge about impedance matching, then we studied in transmission line theory stub matching, कुछ ऐसा करके था. This is called stub matching. तो आपको इसकी लेंथ, स्टब की लेंथ और ये लेंथ कैलकुलेट करके आप 50 ओम पर लगा दोगे तो आपका एग्जैक्टली रिफ्लेक्शन उतना ही होगा जितना आप चाह रहे हो यहाँ पर, और वैसे का वैसा यहाँ पर. That is what you want to do. Now next. Yes, so what is given over here? Gamma S you have calculated, this was coming over here. So as I said, this complete line जो assume करो एक है यहाँ से लेके यहाँ तक 0.5 हो गया, तो ये इतना मैग्नीट्यूड है वो अराउंड 0.26 हो रहा है, और ये इसका जो मैग्नीट्यूड है 0.267 हो रहा है. Both you have calculated, you got two very important values for which you are doing or struggling since last 1 hour. Okay, then you have to make this matching circuit towards the source side. ये बनाने के लिए मैं आपको फिर एक शॉर्टकट बताता हूँ. आपको ये वैल्यू पता है, राइट? What you can do, you can make one circle of this radius. आप assume करो from here to here it's 1, तो 0.2 की रेडियस इतनी होगी, तो आप इसको ऐसे करके पूरा सर्कल बना. Right? Number one, you have drawn one circle. Then this angle was 145. So ये angle वाला 45 यहाँ पर point locate कर दिया. आपका this refraction coefficient what you calculate gamma S, this is locating over here. Now you need to calculate the stub length. What you are looking for this one. ये 50 ओम की लाइन ली, ये भी 50 ओम की ली. अगर आप कैलकुलेशन exactly करते हो, then you are going to get exactly reflection coefficient 0.26. How to calculate this one? We will calculate in two parts. In first part we can calculate length of this stub. In next we can calculate length of this line. Okay, for that what you need to do? Initially क्या करो, आप ये point लो and this assume unity circle. एक circle यहाँ पर ऐसा आ रहा है जिसका ये 1 से क्रॉस करता है, यहाँ पर 1 point होता है. That is called unity circle. So you just look this matched point over here and try to find out where this circle is cutting the unity circle. Locate that point, reach that point, and using this point you just move along the constant reactance circles. Go over here up to here and you locate this point. And how much length you are getting in the terms of the lambda from here to here, that is your length of the stub. As a Smith chart, I can say if you are moving from this point and coming again at this point, that is called half wavelength. Okay. So accordingly, आप बोलोगे ये पैरामीटर कैसे पता चले? ये वैल्यूज यहाँ पर दे रखी है, यहाँ पर 0.0, 0.05, 0.6, 0.07, 0.08. All those values in the terms of the lambda are given. What is lambda? Lambda you have to calculate at your desired frequency. Here you are doing calculation for 8 gigahertz. So there you can calculate lambda. So accordingly you can calculate the stub length. From here stub length आपको मिलती है. आपको अब कौन सी लेंथ निकालनी है? ये वाली. Exactly आप क्या कर रहे हो? आप L टाइप का मैचिंग नेटवर्क बना रहे हो using let's say inductor and capacitor. So arrow is going to fulfill requirement of this one, L type of impedance matching. Okay, then I need to calculate length. This length is how much I want, so that I get exact impedance matching. So after once you do this one, what you need to do? Find out the mirror image of this point over here, and just draw one line from here, getting mirror image. Okay, then what you need to do? From this point, you draw one arc over here, and move from this point to this point, and you take that much length. And that is going to fulfill the requirement of this capacitor, and you will get over here. Okay, so this is called matching circuit at input side. ये आपको पूरा का पूरा ऐसे कैलकुलेट करना पड़ेगा. अगर आपको इतना रिफ्लेक्शन कोएफिशिएंट चाहिए तो इसको एग्जैक्टली इतना ही बनाना पड़ेगा. Otherwise you are going to get some different value and mismatch will happen, and different type of gain you are going to get. Okay, similar type of phenomenon you have to adopt for output side. You want output side reflection coefficient this much at 20 degrees, so same phenomenon. 0.6 का यहाँ पर सर्कल बना दिया, यूनिटी सर्कल को लोकेट किया, वहां तक चले गए, वहां सिस्टम की लेंथ निकाल दी, राइट. देन इसका मिरर इमेज यहाँ पर निकाला, और फिर वहां से लेके यहाँ तक इसकी लेंथ निकाल दी, और ये बना दिया. Okay, once you do this one, your transistor or your amplifier design is looking like this. In एक साइड में इनपुट इंपीडेंस मैचिंग है, दूसरे में आउटपुट मैचिंग सर्किट है. ये आउटपुट इंपीडेंस मैचिंग नेटवर्क, इनपुट इंपीडेंस मैचिंग नेटवर्क, एंड दिस इज ट्रांजिस्टर पैरामीटर. So transistor's complete gain, transistor complete design or its desired gain value is going to depend upon all these parameters, not only on transistor. ट्रांजिस्टर को सिर्फ खरीदने से और उसकी वैल्यू का सर्किट बनाने से रिक्वायरमेंट फुलफिल नहीं होती. You have to deal all those circuitry, and then your requirement is going to get fulfilled. Fine. So this is circuit now complete. Circuits look like this, and this is what you need to make. Now he will show demonstration how to do this. Okay. इसके अलावा और भी स्टोरी है. कौन सी? इसको बायसिंग करने वाली, वो अलग स्टोरी है. Okay. So this is just what you have done. You have assumed that from somewhere you are getting power, but biasing story is different. Okay, fine. So once you do this one, you have to make circuit like this, and you can get all those parameters. Up से directly आ जाते हैं, but many things you have to do again in order to make very workable or practical amplifier. Simulation के लिए इतना करोगे तो हो जाएगा. Fine. So कुछ IC भी आती है मार्केट में अवेलेबल. सीडी परचेज करके सीधा बनाना स्टार्ट कर. ओके, सो EDC में जितना बड़ा था वो इतना RF फ्रीक्वेंसी में नहीं सफिशिएंट है. You have this is additional knowledge in terms of the S parameters, and then you have to start designing. ओके, ये नॉइज सर्कल्स वगैरह मैं थोड़ा स्किप कर देता हूँ, नहीं तो ज्यादा हो जाएगा, सब बोलेंगे. ये तो थोड़ा सफर ही चल रहा है. वो वापस कभी बुलाएंगे नहीं. आपको बहुत सारी चीजें देखनी होती है, फिर एम्प्लीफायर परफॉर्मेंस वगैरह देख सकते हैं. यस, सो हाँ, you can design the amplifier using AWR, and he will show one by one. Before that, I will show some slides. So here we are going to take this transistor what initially I showed by Infineon. Recently I purchased also, so right now I don't have. Otherwise I could have shown you. Only very small this one, like very small. So using this transistor, we are going to make one design using AWR. This is the AWR window. You will see, and here you will have some library options. From there you can get different type of components. एक quickly हम बना के बताते हैं आपको. File manager, ये one by one he will show you. Okay. Then you will get results like S11 अगर आपका -10 डिग्री से कम आता है तो मैच दे. ये पूरा ऑप्टिमाइज नहीं है. Then S22 भी देखना है आपको, S21 देखना है पावर कहाँ पर जा रहा है, कितना जा रहा है. So maximum power you are getting over here, and how much gain you are going to get, and so on. So these results ultimately you have to see. Okay, Rohit, you can show when slowly. So it's not very difficult. He learned within a few hours. We trained him. We trained him for a year. Because initially we were struggling to import the libraries of S11 parameter and other things. So AWR क्या करता है आपका जैसे किसी कंपनी का ट्रांजिस्टर ले रहे हो तो उसकी डेटा शीट को सीधा लोड कर देता है and then it will give you value of S11, S21 and all those values all together. But before that you have to calculate impedance matching circuitry and all those parameters. आप अपने लैपटॉप में बता दो एक काम करो लैपटॉप ही कनेक्ट otherwise here again library and other things you need to install. So here AWR is available. You can utilize. What Deshkar? Feeling very happy. I know it's been tricky and a lot of efforts required. I try to cover many things in less time. He will show demonstration and then he will share some videos so you can do it. Otherwise it won't be possible. Because hands-on thing require 1 day. 2 hours you can.
Do I have to make another one?
We have to make?
Shall I make another one?
No, you can, if you can make, you can make. You can put in front of it, reaching.
But it's, those are like, the cables are right.
Girls will take na cable.
Should I show them from scratch?
Scratching, we can show it will be good. So you can see this window. First, what you are taking?
Schematic diagram.
Okay. Okay, new schematic diagram he is taking. You can write comments. Okay, so this is a window what you got. We are assuming that all value you have calculated. Calculated value means what? Which value you have calculated? आपको ट्रांजिस्टर डिजाइन करने के लिए सिर्फ गामा एस और गामा एल ही चाहिए. उसके बेसिस पर आपने क्या डिजाइन क्या कैलकुलेट किया? Desired gain you have calculated, and for that purpose you have calculated how much gamma s you want, how much gamma l you want. That is what you have pre-calculated. We are assuming like that. So we will drag over here one transistor and other circuit component and उसको feed कर दो. अब कहाँ जाएगी value? That's all. Software portion is not so much difficult. If you have doing practice 2 to 3 times, it will get solved. But before that, fundamentals you must know. If you don't know fundamentals, then many things you won't understand. For example, if you are not satisfying that what I showed M, if you're not calculating M, where your transistor is going to be unstable, that problem you will never able to identify. और आपका रिजल्ट बहुत अच्छा आ जाएगा. आप सोचो बहुत बढ़िया ट्रांजिस्टर और ये एम्पलीफायर डिजाइन किया है यूजिंग सम ट्रांजिस्टर. So those things you have to take into consideration. Okay. So amplifier design करने के लिए all parameters you have to take into consideration and then only you can design. Okay, next. So he has taken here some transistor. A transistor we are taking same what I showed in previous slide, some infineon transistor, and it's why this fellow is important, because it's a S parameter we know, S11, S21, S12 and S22. All those parameters are fixed by company. Those parameters are already available. We nothing to do with that. So he has taken this one. And its biasing condition and all these values you can change. आपको करंट इसमें इस पे रेंज दिया हुआ रहता है. How much range you can give for biasing. All those parameters you can give as per standard. ये कितने गीगाहर्ट्ज का 8
8 gigahertz.
Yes, transistor works up to 40 gigahertz. But MOSFET are good options. MOSFET or open IC. With the help of that, you can make very easily because some integrated portion is there. Because you know, OPAM always give better noise capability due to high input impedance. Transistor का भी high input impedance होता है CE configuration में, but इतना ज़्यादा नहीं होता जितना OPAM का.
This transistor, BJT and op-amp supported.
No, BJT is transistor only.
Yeah, but
नहीं op-amps RF पे चलते ही
नहीं, OPAM है सर तो.
बहुत ही रेयर है
हाँ.
क्योंकि एक op-amp मतलब कम से कम 10 ट्रांजिस्टर
हाँ.
तो वो उसका नॉइज और ये वो इतना रहेगा वो रहता ही नहीं.
तो जैसे अगर आपके पास एक ट्रांजिस्टर है that giving 10 dB gain and you want to design for 30 dB, what you will do? You have to do cascading. So same fundamental पढ़ा है ना BTech में. Same thing we have to do. We make one transistor की input दूसरे में दे दो, output उसकी अगले में दे दो. Then you will get that much because gain is A1 multiplied by A2 multiplied by A3.
That is why in RF ऐसे single transistor circuits ही अभी भी चलते हैं. op-amp को अगर हाँ op-amp को अगर वो low frequency instrumentation biomedical इधर चल रहा है. यहाँ पे ऐसी एक या ज़्यादा से ज़्यादा 2 ट्रांजिस्टर का सर्किट.
But in RF, in place of capacitor and inductors, if you using microstrip based circuit, then it will be less noisy and it will get accurate value also. Because at high frequency, capacitors and inductors are going to be very lossy and abrupt behavior as well. Because transmission line will come into picture. So 5 gigahertz से नीचे ठीक है. If you go beyond 5 gigahertz, then you have to use Kuroda identities and J inverter and K inverters. Whatever capacitor and inductor values are there, you have to convert into transmission line. Then only you can.
That means you don't get good quality passive parameters at those frequencies.
Yes, exactly. For example, if you want inductor value 1.3 and nearby value is 1.1, then what tolerance you are getting because of 0.2, who will compensate? But transmission line, exactly, you can get 1.354 even up to 4 decimal exact value you can get.
कितना नैनो हेनरी की कोई
वो उस particular value में नहीं जा रहा. What I'm trying to say is,
सिर्फ accuracy.
you can get very accurate, exactly whatever accuracy you want, you can get it with the help of microstrip.
Adjust proper focus.
हाँ.
Width you always keep 50 ohm. Length and other things, stub things, you can change. Because you ultimately you are going to feed your amplifier with the help of 50 ohm SMA connector. So it's a good practice, keep 50 ohm initially.
How much is remaining?
Yeah, just a minute.
Otherwise, I think otherwise we got the feeling how it is to be done. So you can share directly the final result. I mean, that is not a problem.
एक आपके पास जो बना हुआ है वो दिखा. It's a very big course or a lot of lectures required for this.
Actually, ना मेरे ध्यान में वही आया कि थोड़ा फिर hands-on का separate रखते थे, वो combine नहीं करते थे.
One complete day required for this.
मतलब हमारे एक ही सेशन में 2
आपको जो दिखाया ना, that is not very difficult. It's very easy only. It's looking like lot of equation, but nothing is there. Only reflection coefficient, and that is also in terms of the S parameters. If you should be master of Smith chart if you are RF designer. You can show directly what you brought now on 5.
That gamma S and gamma L part just to show that how it is that stub or transmission line वो कौन सा है वो
See what you are seeing over here. This is called biasing. Okay, ये biasing है, voltage divider biasing जो generally है to feed or maintain transistor in operating condition. What we call large signal analysis. उसके थ्रू जो लोड लाइन कॉन्सेप्ट वाला है वो ये शो कर रहा है ट्रांजिस्टर रिमेन्स ऑलवेज इन ऑपरेटिंग कंडीशन। ओके, जब ट्रांजिस्टर ऑपरेट रहेगा तभी तो गेन देगा। सो वी आर नॉट कंसीडरिंग दिस वन, वी अज्यूम दैट ट्रांजिस्टर इज ऑलवेज इन ऑपरेशनल मोड और ऑपरेटिंग। ओके, now what I said, at input side you need stub, this one, right? This stub you need, this one, and then this one, and you have calculated its length. So here by clicking over here you can put its length directly at that particular frequency, and this is going to act as in parallel and this is in series. So ये इसको इसके पास जाके लगा सकते हो आप ऐसे टेढ़ा में, ये इधर लगा हुआ है। So it's कहाँ चला गया? Okay. You track from here. Okay. Okay, so these are just stub at the input side, which is called matching circuit. These are responsible for giving particular value of gamma S, input side reflection. Because when you calculated the value of gain, it was consisting of three components. One was GS, then total G, other side was GL, right? So this is satisfying this condition 1.37 जो आपने बताया था, and then this is satisfying other condition. So here you are seeing again matching circuit over here, this one and this one.
So input and output matching circuit will get developed with the help of transmission line.
I showed like that only.
Yeah, like that only. So it will.
You can make even L match. L match you can make.
And remaining part will be we'll be taking transistor and then biasing.
Biasing is a standard one. Biasing nothing to do with gain.
Yeah.
Biasing you need to maintain transistor always operational. आप उतनी power transistor को दोगे तभी तो transistor operational mode में रहेगा ना। इसके पास एम्पलीफायर के पास वो जादू थोड़ी वो सिग्नल को बढ़ा रहा है, वो आपकी बैटरी से तो वैल्यू ले रहा है। जो एनर्जी है वो कहाँ से ले रहा है? जो डीसी वैल्यू जो आप दे रहे हो ना, उसी की वजह से सिग्नल बढ़ रहा है। What value signal is going to amplify? It's taking value from DC battery, or what DC you are providing over here. So with the help of that, it's going to get amplified. So this always you have to maintain in such a way, load line आपकी बिल्कुल बीच में होनी चाहिए। Otherwise transistor off हो गया तो ये कुछ भी नहीं करेगा, ये भी कुछ भी नहीं करेगा, right? So this is set in such a way, voltage divider ये जो biasing है, it's most stable one, you know very well, right? Huh?
Lumped components will be using it.
These are lumped only, no?
Yeah, so this here we will be having on input side and output side a transmission line, and for biasing we will be using lumped components and then
Yes. I showed like that only, that's why I'm.
No, actually just now he mentioned one point which perhaps was not shared with all of you. Actually, when we go, suppose you, I think your question is why not implement the matching circuit also with LC lumped components, isn't it? I think that was the question.
Yes, that is what happened.
So the answer is that many times it happens that you don't get lumped components of all the values. You get them of only certain values. So if you don't get the exact value that you need, then again you are not achieving the desired result. But the advantage of implementing it with stubs and all is that you can accurately decide the dimension and you can achieve that also. So that is the advantage with.
Reflection coefficient उतना रखना ही है अगर आपको exact वो gain की value चाहिए.
So that is possible with transmission line implementation. So space-wise, transmission line takes quite a lot of space compared to discrete components.
So sir, inside mobile phone, the modes which we develop, so is similar kind of technology used?
Yeah. And actually, it is not. This is only the story has only started actually.
You can make complete IC of this one. सारी चीजें एक के अंदर डाल दो तो IC बन जाएगी ना. You can complete make one encapsulated quantity. Directly आपको सिर्फ यहाँ से input दिखेगा, यहाँ से output दिखेगा.
So resistor and biasing part that will be inside IC, sir.
You can keep inside.
Matching network will be
Then
outside.
IC, if I am showing IC, what you will see over here? We have to spread and show you, no? Then only you will understand how things are happening. IC is only integrated thing, no? So you will see only box color.
This circuit is still at schematic level. when it is translated to some physical
Practical implementation.
means physical design. Transit means suppose now this is the board level design. So you do the PCB track and all the components are installed. Then you get parasitics associated with your physical implementation. Those parasitics should be again represented in this schematic, and schematic will change. And again you have to simulate. And then that performance also should be acceptable. Okay. And after that, if it is a product, then it has to undergo Monte Carlo simulation, because there will be variation in resistor value, there will be variation in stub length. So will it survive that? Okay. And if it is chip level, then you have to also do thermal simulation, that whatever is the temperature variation for that particular circuit, will it work over the entire temperature range? And when all these things are taken care of, then it goes to tape out or whatever. So this is only beginning of the story. So I think are we done? Okay. So thank you for your patient listening. I realized we could have split it into 2 sessions. But anyway, if still you think that something hands-on can be done, Rohit and Arvind can come again and you can focus only on the hands-on part.
Presently, if some videos can be given, sir, then it will be better.
I will talk to Arvind next. So thank you very much.
Thank you, sir.
Thank you so much, sir, for such a wonderful session, starting with all the beginning parameters, the S parameters, and complete design of the amplifier circuit. And as rightly mentioned, we will definitely have a complete hands-on session for a day, complete day session, so that participants can make more benefit of it. Thank you so much. I request Dr. Sanjini Shastri ma'am to felicitate Dr. Adil. Thank you all the participants. Tomorrow we will be starting with the session at sharp 9:30. Thank you.
Please call him.
Not required. You have formula outside. You know process knowledge. That is not our way to remember formula. We have to know formula for value. It was pretty like that because when the lot of slides were there. That's why I just suffered slide. That's why it was looking for. Otherwise, that guy did know. He attended all classes and he showed me demonstration. Even I never teach them this AWR. I just taught theory. Everybody made this. So it is not so much difficult. Even I don't know much AWR, but he knows very well. I have given assignment to design this amplifier, power divider, and branch line coupler using AWR. Somehow,